All right, hi everybody, thanks for coming. My name's Jonathan, and let's talk about virtual functions. So this talk is about eliminating virtual, and so I think before we can do that, we need to discuss when virtual is useful. Fundamentally, I think this breaks down into three cases. First, requiring a specific interface. So you can use a virtual base class. You can require that a function with specific properties exists on an object, right? This is a natural use of a virtual function. Those virtual objects are useful for configurability. So if you want to switch the behavior of some class, you can hold a function to a virtual base, and then depending on the derived type it holds, the usage of that object that's holding the virtual base will differ. And then we can also use them for holding multiple different derived types within a shared base class in a single container. So ultimately, these are going to be the three things that we're targeting here. With that said, these are useful things, right? Like why would we can already do all of these things? Why would we want to do them differently? So first of all, to use virtual base classes, you essentially need to use pointers. That indirection is not necessarily bad, but it's forced upon you. There are cases where you don't want it. So with a different approach, we can eliminate that. We can also capture our system properties more statically. Why is that good? It helps to move errors forward. So for example, if you don't have that pointer, you don't have to worry about null pointer. If you're not storing in some base type, you don't have to worry about incorrect downcast. These are runtime errors that we can move to compile time or eliminate entirely. Also, more static description allows the compiler to see more deeply through our programs, which is going to open up opportunities for optimization. With that, we get greater flexibility in our design. This allows us to have additional avenues that we can explore for implementing the same kinds of things we might be implementing a different way. Whether or not that makes sense is a decision that you guys have to make as software engineers. I'm not going to stand here and tell you that what I'm about to present is the only way that you should do this and that you should never write the virtual keyword again. I don't think that's true. This is an approach for you to consider, and if it makes sense, right, we're gonna discuss all the trade-offs that are associated with it. It can improve performance. I don't know if anyone caught Evika's talk this morning, but Evika did a whole talk on this, so I'm not going to cover it at all. I'll brush on some of the mechanisms by which performance is increased, but in terms of actual measurements, Evika has done a much better job than I will be able to do in the time that I have. He also has a great blog post on Johnny's Software Lab. If you're not familiar with Johnny's Software Lab and you're interested in performance, check it out, especially his post on virtual. And also because we can, right? Like I think this is a fun thing to consider. It's an interesting mental exercise, just in terms of trying to consider how we write code, why we write our code the way that we do. I think there's also some implementations that are potentially, immediately obvious that I'm going to ban for the context of this talk. So recreating anything that's like a vtable is not going to be anything that I touch on. I don't think that that's in the spirit of the talk. And frankly, I haven't benchmarked this, but I'd be surprised if it ended up faster. Like the hardware machinery for vtables is really good. I think the best hope there would be that the compiler sees that you've re-implemented a vtable and give it back to you. And then type erasure, same set of concerns, right? So let's talk about binding interfaces. So the format of this talk is going to be, I'm going to show you a virtual implementation of something. We'll talk through, why it looks the way it looks, and then we'll go and we'll look at the implementation without virtual. As we're going through here, anything that ends in interface is going to be a pure virtual class. If you have some template type, it's going to start with T, and then concepts are going to be prefixed with C. Hopefully that'll help you keep straight some of the naming soup that we end up in. So here we've got a base class. It binds the function. It binds a function func with a return type of int, and then we have an implementation of that. We just called foo. Hopefully this is not anything that's surprising to anybody. In general, I'd say this is pretty clean. Unfortunately, we have to deal with rule of 5 here. We end up needing virtual destructors, which means we need all of this other stuff. In at least some cases, you're not always going to require this, but there's a decent amount of time where you do, and that ends up being a bit less clean. So let's say we want to do this without virtual. Again, remember that types are T whatever, concepts are C whatever. So we've got a concept here that's going to bind our virtual interface. And you can see here we've achieved the same thing that we had with the virtual by using the concept to bind. You can use the static assert to ensure that a particular class conforms to a concept. In general, I'd be surprised if you need that in your main code. I'd expect that you'll mostly want that in test code if you want it at all. And instead, what I'd expect is that you'll want to apply the concepts to your interfaces. Here, because we don't have any virtual anything, we get to rely on rule of 0 instead of rule of 5. I will call out that concepts are a C++20 feature. If you desperately want this and you don't have C++20, you can achieve this with enable if, but it really sucks. And it sucks a lot harder as you start to increase the complexity, which we're about to do. So you also get an additional piece of functionality here, which is that we can bind more loosely than we can with a virtual interface. With a virtual interface, we're kind of restricted to binding to some concrete type, whereas here we can bind to a concept. I don't think there's a way to recreate this in the virtual machinery without layering concepts on top of it, and then you end up, you've got foo interface and C foo, and you have to ask yourself every time you implement something, oh, do I also put this in the concept? It ends up, there's additional cognitive overhead for the developer, and it ends up not very dry. So this is where we end up with our usage. You can see here with virtual, we've got a good amount of pointer use that kind of clutters the potential meaning of the code. And then in the case without virtual here, it's just simple object creation and passing. The only thing that's maybe a bit unexpected for those of you who haven't used a lot of C++20 is the concept on the function. Does anyone have any questions on this before we move on? Okay. Sorry. If you could come up to the mic, or I can repeat it if it's a pain for you to get out. Yeah, go ahead. So I'm not sure there's a question there. The statement is, so the statement is that the virtual function is using dynamic dispatch and this is using, they're not equivalent in terms of mechanism, I agree. But in terms of function, you can't, so the statement is you can't do, we're going to get into that actually, so stick with us. The comment there was that you can't pass this around at runtime without knowing its type, and we're actually about to cover that.
There is one question from online audience.
Sure.
Is there any way to store a list of objects that all satisfy the CFU concept?
Yes, we'll cover that shortly.
Okay, thanks.
Okay, so you guys are ahead of me. Let's talk about owning polymorphic types. So here, our case with virtual, we've got a type bar that can hold some type foo. Worth noting here that we're explicitly not going to cover how to change this at runtime yet. I want to cover the case where this is static at compile time, and then we'll proceed into that. Here, I think pretty straightforward. You take input foo and you just store it in the class. Hopefully nothing too surprising here. So without virtual, we can templatize this class, and we can templatize this class on the member type, and then we don't actually have to name this type when we use it because of CTAD, and then we just take that type, we store it from the constructor. Again, I'll call out the major difference here is that our type cannot be changed after compile time. As some of you have probably noticed, this doesn't actually bind that we conform to the interface foo, where in the previous case we did, right? So we can make a modification here, and we can constrain the type of the class to our concept cfoo. And now we're back to what I would say is a pretty functionally equivalent implementation with all of the benefits that we gain from concepts in terms of more loosely binding, that sort of stuff. So let's talk about what we want to do if we want to manipulate things at runtime. So we're going to go back to our virtual implementation. Nothing here has changed. And we're going to do, again, what's hopefully the obvious thing, and we're going to introduce a function set foo. Really, it's pretty much identical to the constructor. We're going to take input foo, we're going to assign it to our foo. And then what you do with this, I don't know, who cares, right? There's a million things you can do. I can't list them all. So let's go back to our non-virtual implementation. So we've got this, right? And we want to add a function set foo. So we can parameterize the class on a list of types that it might hold. And we can keep that constraint on cfoo. That means each of the types that's provided must conform to cfoo. And then for storage, we want to be able to store one of any of these types, right? That's the semantic that we had previously. We can do that with a variant. We do have a little bit of a hitch here in that we now no longer know outright what the types of our functions are going to be, the input types of our functions. We can switch those to auto. That'll take anything. But we end up with a problem here where you're going to run into a really nasty template error if you try to assign something to this that the variant doesn't take. It'd be really nice to get the concept error instead. So let's go about that, right? So perhaps the obvious thing to do here is to apply the concept constraint to the functions. I would argue that this is not the correct decision. If you consider the set t foos and the set of types that conform to cfoo, not every type in the list t foos is necessarily in the set of things that conforms to cfoo. You could potentially end up with foo1 and foo2 in your type list, and then foo3 passed in, and you're back to your ugly template error. So let's unwind that, right? And let's think about what we actually want here, right? What we actually want to say is we only want to accept types that are in the list t foos. Once it's in the list t foos, we know it conforms to cfoos because we've applied the concept as a constraint to that list as a whole. So we can write another concept. I've called this concept same as any. I make no argument that that's a wonderful name. But we use the facility stood same as, which is a concept that compares two types and just evaluates to either true or false. And then we do a fold over a list of types that we provide to that concept. And if any of those types evaluates true on same as, then we know that one of the types in the list is the type that we provided. So we can then apply that. To our functions and say if the input type is in the list tfoos, we'll accept it. Otherwise, give a concept error, and those are nice and pretty. Hopefully, you guys have seen a couple of those by now. So this is our final design here for runtime. If I saw this in code review, I would posit the question as to whether or not this is good design. So the first thing that stands out to me here is that we're using variant, and variant has runtime cost. When you go to do any operation on a variant that needs to know the underlying type, that's a runtime lookup. I don't know every domain that all of you work in, but for the domains that I've worked in, embedded systems, high performance computing, that sort of thing, it's difficult for me to think of scenarios where this type couldn't be known at compile time. They probably exist. I'm not saying you don't have that, but I would urge you to think carefully about whether you do have that scenario or whether you could be more clever with your type passing to get this to the point where we can actually use our previous implementation. This might be necessary. This might be something that you need to do, but generally I wouldn't reach for this without a good reason why you can't do it in a more static way. So let's look at our implementations here. In our virtual case, fairly clean. We've got this extra make unique. Personally, I'd prefer it if we didn't have that. It clutters things a little bit. Without virtual, in the runtime static case, very clean. Like, I don't think you can, I think that's like the platonic ideal, right? In the case where we want runtime dynamic, we do have to provide the list of types. If we really need it, we can hide that list of types behind a using, and that simplifies things. And I'll show an example of that in a little bit, but generally speaking, I think, not bad, probably about equivalent to the other case. Any questions? Yes.
Well, so kind of similar to this doesn't do exactly what virtual does, and it doesn't do it in two ways. One, you just pointed out, the virtual equivalent of this will take any full interface. This thing takes what's listed in the variant and not what passes the concept.
Yes.
So they aren't doing exactly the same thing, and if I wanted to take anything that satisfies full interface, whether it's written or not yet written when I'm writing this class, I can't do it this way. And the second one, make unique, moves from unique pointer, which is always works. The second version moves from the object, which may actually be copying, if the object is not moving. Again, it's not doing the same thing.
Yeah, so two comments there. One is that in the runtime dynamic case here, we must explicitly list our types. If we were to add a type at some point in the future, we write this code and then we go and we add foo3, we have to update this to add it to the list. And then there's a concern around whether or not the make unique guarantees a move of the pointer, whereas you're not necessarily guaranteed the move in the case without virtual. I agree with both of those concerns. Again, this is a potential alternative approach. I don't think this is necessarily always something that you should reach for. Like, for example, if you have, say you're writing some code that you expect a user to extend, there's no possible way for you to know all of the types to supply to this list to bar. And in that case, you're precluded from using this approach. It's not, again, like not something that can apply equally to every domain, but rather another tool for your tool belt. With respect to the concern around the moves and copies, again, I agree. I think it's something where I would expect that a lot of the underlying code here is going to be written carefully once to handle that set of cases. And, the same way that make unique has been written carefully once to handle that set of cases. And if you have objects that you want to ensure aren't copied, you should delete their copy constructors and not rely on your downstream machinery to do the right thing. Does that feel like a...
Well, yes, but then this just wouldn't compile, whereas the make unique would be perfectly happy to compile and do what you expect.
You could, so the comment here is that if you delete the constructors, the copy constructors, this just won't compile. This can be made to compile if you start taking things by forwarding reference, etc. Yeah. I just for the sake of the simplicity of the slideware, I didn't want to. I'm trying to think more about the concepts and less about the implementation. Sure, go ahead.
Just one question. I haven't thought this through, but this does also have an impact on code size, right? So if I have a function that takes that expects var, and in one case it just I think it has an impact on code size, right?
Yeah. So the question is whether or not this has an impact on code size. Yes. There are absolutely cases where this can significantly increase the size of your generated code. Again, whether or not this is a sensible trade-off falls to you as developers to consider. I've dealt with a lot of I worked in the IoT domain for a while, and like building things that coordinated communication between IoT devices. And with that, we could safely take this approach, and we had like one list of devices that we supported, and I would be surprised if it significantly changed the binary size. Whereas if you need something that's going to take various subsets of this, you get another instantiation of the function for each additional, and then at that point you're relying on your linker to try and notice that those are the same and unwind them where it's possible, which is I don't know, linkers aren't great, I guess is the summary. Any other questions? Yeah.
Yeah, line 2.
So that's a fold expression. So you might be more used to seeing this. So the question was, how do you interpret the ellipsis on line 2? You might be more used to seeing this the other way around. So it stood same as or ... David Stone convinced me to write it the other way around because there's an ordering concern, and this does things in the order of the list, whereas if you write it the other way around, it does things in the reverse order of the list. And I've been confused by that a couple of times, and I got annoyed with being confused by it and got in the habit of writing it like this. Any other questions? Sure.
I'm going to show a benchmark later, because the reason I'm asking is I actually benchmark GCC's variant against virtual function. And depending on what you do with the variant, sometimes it's faster and sometimes it isn't.
So the question is there a benchmark? Evika gave a talk this morning specifically covering performance implications of virtual. I'm gonna avoid recovering that. I'd be happy to sit down with you and write some benchmarks afterwards. That was fun at CPP Now. We can do it again. Yes, yeah, and so the comment is the performance implications of virtual are clear. The performance implications of variant are less clear. I agree. That's why I would say carefully consider if this is if the runtime version of this is something that you want to reach for. I actually put this in here as kind of a negative example where you move away from static properties by virtue of like lack of compile time knowledge, so that you must consider whether you can find a way to have better static knowledge at compile time. Anyone else? All right, awesome. So let's talk about storing multiple types. So we have some container baz, and it's going to store some collection of varied foos, foo1, foo2, etc. As of C++23, we could make this const expr. Unique pointer is const expr in 23. I ran out of width on my slides. Pretend like it's there. So I think this one ends up being a little bit more complex. So I want to talk about the properties that we're looking for here before we dig into the implementation. So as with before, we need to know a list of the types. That's kind of foundational to this approach. Ideally, we want to deduce those. Here, we're not going to be able to, unfortunately. We need some container that can hold many different types simultaneously. Hopefully, when I say that, everyone thinks tuple or something along the lines of tuple. And then we also, if we want to hold more than one of a specific type, we need some container that can hold more than one of a single type, right? So a vector, a list, array, hopefully everyone's thinking along those lines. And then if we were guaranteed one of each, you might want to reach for something like optional, but I don't know, that I can't think of a use case in which that would be relevant, but if you have that use case. So let's look at an implementation without virtual. So we've got a container. It's parameterized on some type list, tfoos. This time we're going to use a storage of a tuple of vector of tfoos. So we have a vector of tfoo for each item in that type list. We've got this store function here, which is potentially non-obvious, right? So what we want to do is we want to look up the vector that's storing the specific type, and then we want to add the value coming into that vector. So here we can deduce our type t from the input type, and then we want to look up the vector holding t in the tuple, and then we can simply push back onto that. For this talk, I'm only going to cover kind of the pushback case. But if you want to, you can write this so that you can write a concept that checks whether your list of types is implaceable. And you can do in place and a bunch of other fun stuff. You can implement pretty much everything in the vector interface for some definition. So you may have noticed we didn't constrain this, right? So we're gonna go ahead. We're gonna add our concept constraint. And then we're gonna reuse same as any, and we're gonna apply that to the type t coming in. So this is our final implementation here, right? Generally speaking, I would expect this to be quite efficient in the case that you have many of each type. You end up with really static locality. You end up with really good locality and a very static description of what's being done in the type system. There's no type erasure. The compiler should be able to see really deeply into this. You do have the overhead of the size of an empty vector per type you use. So in our virtual case, there's one vector. Here we have n vectors, where n is the number of types that you're storing. There's also an interesting kind of, I don't know if it's good or it's bad. It's just an interesting property of this, that your ordering is not stable. Here, your ordering is stable within a single type, whereas in the previous case, your ordering is stable across all types. So if I were to insert a foo1 and then a foo2 and then a foo1, I would get the first foo1 out of the vector in the order that the foo1's out in the same order, but I wouldn't know when the foo2 came in relation to those without adding some additional metadata to capture that information. So let's look at our implementations here. With virtual, fairly clean. Again, we've got those calls to make unique, which we've been seeing pretty consistently. Less than ideal. Without virtual, we've got our type list again. I wish that would go away, so I made it go away with a using. In a lot of domains, you're going to have one fixed list of types that you're handling. If you store that one place, you can kind of make this look like none of this is happening at all. So at this point, we've kind of covered how the general techniques that we're going to use, and we're going to take things up a notch in a second here and start trying to apply this to some examples. So does anyone have questions about storing multiple types or any of the previous things? Yeah.
Stable ordering across types, I didn't get that. Like between foo1 and foo2, why are we losing the ordering?
So the question is, why don't we have stable ordering across types? So because we have a bunch of separate vectors, our ordering is consistent within each vector, but the order in between vectors is not knowable without some additional information. So you could keep some sort of order parameter and store it in the vector, and then you could reconstruct the order if you wanted to. But if you don't want to have any storage overhead, you lose that information. Yes. Any other questions? Okay, cool. So let's just review quickly before we move on. So we're going to use concepts to bind interfaces instead of virtual base classes. We're going to use deduce class templates to provide compile time configurability of contained objects. And we can use stood variant to achieve runtime configurability if we need to. Again, I would not argue for that. Oh, and I lost a bullet point. The third bullet point there is supposed to be that we can use something like a vector of tuples, or a tuple of vectors for multi-type storage. So let's talk about some downsides here. This approach is naturally going to increase the size of our translation units. In the case where we have virtual, most of the time you're only going to need the base class. Here, whenever you're passing around one of these containers, you need all of the information for every type it contains. In some domains, that's going to be a lot of types. As we discussed, we have a potential increase to the binary size here. As you start to instantiate more types, your binaries get larger. There are cases where the linker solves this. There are cases where the linker doesn't solve this. If you're not running with aggressive, like with LTO, those sorts of things, expect your linker to not solve this very well. With that, you're probably going to get an increase in compile time. As you have larger TUs, as you have more code in scope, you're just naturally going to need, the compiler's job is heavier. You're going to need to use more memory. You're going to need to do more computations. Right now, compilers aren't really designed to compile fast. This is something that I think is starting to be worked on, but for the most part, they're designed to compile code that runs fast. I don't think this is a fundamental limitation. If you guys have played with Circle, Sean's implementation there seems to compile much faster than anything else for the same feature set and similar generated code. I think that we can probably address this with engineering focus, but right now, if you go and use this, you could see some pretty significant compile time and compiler memory usage. And this may add complexity to your code. Depending on the level of comfort of your coworkers with metaprogramming, these sorts of techniques, this could create something that's difficult for other people or even yourself to maintain. We talked about the upsides, right? Like these are the downsides. These are the things you have to consider when you want to make whether or not you want to make this trade-off, right? Which you're ultimately making to some degree for better performance and for that clearer type system information. So with that, I'll make a bold claim. As of C++ 20, I don't think that you're ever required to use virtual for binaries that are built from source. I'll point out that this does not count anything that uses dynamic loading when you start linking in code, especially code that you don't have access to at the compile time of the original binary. This goes out the window. But I don't think you ever need virtual. Whether or not you should use virtual, again, is up to you. You need to make that decision. I'm not saying you should, I'm not saying you shouldn't. I just think you don't have to if it doesn't make sense for your domain. All right. Questions on that? Yeah.
I'm going to throw a counter bold statement.
Please.
Under the same restrictions, all the types are in the header, and all the types are known in compile languages. With virtuals, you may be writing code for the type that hasn't yet been written.
I agree.
Without virtuals, so all the types are in the header, and all the types are known in compile language. The compiler should be able to devirtualize everything completely. And if it doesn't, it's, as you said, transient state compilers are getting better. With GCC 11, look up the bug report of the tree with long term. GCC 11 devirtualized some weird thing that, I don't know, I wouldn't have figured out that it can be devirtualized, and it did.
So Fedor's comment is that if all of the types are available, as they must be if you take this approach, there's some world in which the compiler is capable of fully devirtualizing through all of this. So I agree that that seems theoretically possible. I don't know. I can tell you that right now, when I do this sort of thing to my own code, in micro benchmarks, I see something like a 2 to 4x improvement. So
But did you actually make apple comparison? Did you move all the types?
yes. Like I'm specifically micro benchmarking. So the question was, are we making apples to apples comparisons here? Yes, I'm doing my best to make apples to apples comparisons and try to understand the implications of this sort of thing. ultimately, I think where the compilers are at right now means that this approach ends up being more efficient. If that remains true forever, who knows? I mean, I'm sure we've got some compiler people in the room who would love to comment on that, and find me afterwards. That sounds super interesting. Yes.
Just one comment to that. I think I'm not sure it's really possible to devirtualize everything because, like, if the compiler may not even know if it actually knows all the objects that go into a specific interface, so that might make it hard. That's kind of your argument that like virtual functions kind of are like virtual code is made for this situation where you don't even really know the set of types. And I think in C++ it's really hard to know for the compiler to know whether they know all the types or not. That's one thing. And the second thing is, isn't the statement that you don't need virtual functions, isn't that kind of, I don't know, moot in the sense that you can implement every system in C. There's no system that you cannot implement in C, so you naturally never need virtual functions. But the question is it a good design choice or not?
Sure. So that was a two-parter. I'll do my best. Part one was that it's not necessarily true that a compiler could fully devirtualize, even given whole program context, because of the like decoupled nature of virtual. Does that feel like, yeah? And the second part there was that the assertion that virtual is not necessary has been true since before C++, because C does not have virtual. I would actually disagree with that. I would say that for that to be true, you end up with I'd be surprised if you could do it without like void star as well, which is type erasure, which is against the rules. I'll go back to my rules slide if you make me. Right. So like which is like ultimately it's crappy virtual, right? Like to some degree, void star is worse virtual. It's like, here's this thing, like don't worry about what it is, and then you pull it back out and like you downcast it by virtue of knowledge, except that you have none of the checks.
But you contradicted your own rules because you basically said don't do jump table of pointers. Variant is, I mean, I could implement variant entirely with virtual, but that's not how they do it. Like if it's in GCC, it's a jump table of pointers.
Yes, I completely agree. And again, that like, so the comment is that I also broke my own rules by using variant, and I agree. Like the variant example is very much to demonstrate how you can be not using virtual and still be pretty close to using virtual. So the comment is that GCC's variant is a jump table of pointers in implementation. Yeah.
So your object list could be based on an input, which is just not known at compile time.
So the comment is very confidently asserted that the compiler definitely can't devirtualize everything, and I'm pretty sure there's going to be a knife fight in the hall afterwards.
No, but just thing. So like for instance, there's a Microsoft talk about like such a huge Office. So Office is built from source. Maybe they built it with that source, but technically you could build it from source. There's a reason why we use virtual, which is because we want to have layers of modules. Like there's a higher level layer which doesn't know about all the types.
Sure. So the comment is that Office, which is a massive code base, is built from source and could be built without virtual, but they choose to use virtual specifically for the ability to not have to know all of your types.
Just have a disclaimer. I don't work at Microsoft.
Oh.
Just like as an example of any like large monolith.
The person who's asserting this would like to note that they don't work at Microsoft and have no knowledge of the Office code base in specific. Sure. So the comment is that if you use something like the tuple of vectors approach, you end up having to redesign your algorithms to work on that data structure. I completely agree. In some domains, we're going to cover an example here in just a minute where you'll see that that doesn't matter. In some domains, that matters a lot. And having a collection of virtual base class pointers may be the most efficient thing that you can do. Again, I'd like to just emphasize that this is not something that I advocate. Just you shouldn't go into your code base tomorrow and grep for virtual and open up a PR against every instance of it, right? You're going to make all your coworkers mad. But B, it's not necessarily the most efficient approach. This is another tool to put in your tool bag to reach for when you have a specific class of problems. Specifically, if you're very latency focused, these are the kinds of things that can be very useful. If you're throughput focused, less so. If you don't care about performance, I don't know, write Python or something.
There's a question from one of the online attendees.
Okay.
How easy or difficult is it to mock these non-virtual subclasses for unit tests?
So they should be fairly trivial. What I've done in the past to solve those sorts of problems is I'll write a fake set of types and inject those and test the containers on their own. And then as long as the types behave right and the containers behave right, everything else tends to work, and your whole program testing should catch it if it doesn't, right? You should unit test those separately. Hopefully that's a good enough answer. Yes? So the question is, did I compare debugging between both of these approaches? I have debugged both of these approaches. I don't know that I'm not the right person to ask about debugging metaprogramming stuff because I've done so much of it that I'm immune to the pain of it. If I can't debug it with print statements, I'm kind of screwed anyways. So yes, it's probably harder, but also I think it's something you get used to. It's a different approach to debugging. Got another one from online.
Yeah, there is a question which references today's morning's talk. The question is, could the tuple and vector implementation of polymorphism still work with virtual and get the benefits of virtual without the locality hit that was discussed in today's morning's talk?
So I didn't catch this morning's talk, so I'm not sure that I can answer that offhand. I'll be if you want to bounce ideas off me, feel free to grab me in the hall. I'm the guy with the mohawk. Or for the online folks, I'm active on Discord. DM me, or there's a channel for this chat. I'm sure some people are already typing in there. Have some interesting feedback. So I'll be in there. I'll be in there after the talk. I love talking software design, so nerd out with me. We'll figure it out.
Okay, thanks.
All right, so practice time. So let's lay out a task. We've got some set of devices that are on the same network that our binary is going to run on, and we can interact with them. We've got no networking restrictions. Each type of device is unique in how we interact with it. So each class of device is unique in how we interact with it. And it's not possible to know the device's connection information before we join the network. We have to figure it out in situ. If you've worked in IoT or networking, this might smell pretty familiar. If you haven't, this is a pretty common sort of problem that people actually are dealing with day to day. So some design considerations here. That design consideration slide got lost when I changed my text color. Whatever. So I'll just shoot from the hip here. So we've got a set of types, right? Each type is going to make sense to discover all of the devices of that type individually, because that's how all of these search mechanisms work in the real world. Once we find those types, we want to store them, and then we're going to want to monitor their state, because that's our like general missive. But when we find those devices, we're going to want to create an instance of each one because like say for example we find a switch, right? That switch can be on or off. Like if the first switch we find is on, that doesn't necessarily mean the second switch is also on, right? They're going to have individual state. So let's do this with virtual. So we have a device interface, right? And that's going to bind that we have some function, find an env, so that we can find all our devices, and then some virtual function update. Anyone see anything about this they don't like? Yeah, it's static. We can't actually say virtual on static, so we can't really bind that as part of our interface. So this is where we end up, and then we're just going to eat the compiler error when that happens, and hopefully we won't make any mistakes. Okay, so let's establish some device types. This is going to be boring. I'm going to fly through it. So we've got a switch here, and it's got an isOn property, right? It's a Boolean, either on or off. And then some update function that's going to go and pull the switch and figure out if it's on. Who cares what that does? And then our find an env function, which is going to find all of our switches. Same for dimmer. Only notable difference here is that it's got some sort of brightness associated with it, right? We're going to pretend that we're going to want to manage some set of these switches and dimmers. And hopefully it's easy to imagine that we could have hundreds or thousands of different device types. But I'm going to keep it to 2 because my slides are this long. So we need a device manager, right? Our device manager, the constructor is going to take some list of devices and store them. And then for our stored devices, when we call update, we're just going to iterate through them. We're going to get all of our devices. It's pretty straightforward, right? We also need a way to discover all of our devices, right? We have to call find an env for each of our device types. Unfortunately, with things as we've constructed them, this is how we have to do it. So we have some, device list, which is a vector of unique pointers, and we go and we call find an env for each of our types, and we update that output. We could use a macro here; it would make things better, but ultimately, this is kind of what we have to do. Anyone have any issues with this? Yeah. Did anyone not notice this? Yeah? One hand. There was only one person who didn't notice this. This is a super easy error to make. I've made this error a bunch of times, right? This is the kind of thing that we really want, the kind of boilerplate code that we really want to avoid. Because every time that someone comes in here and adds a device and copies and pastes this thing, there's a, some % risk that they forget to update this, and this happens, right? And then you're like, why isn't this very specific thing showing up? And maybe you don't notice it for a couple of months, and this is a hard bug to find. All right, so we fixed that, right? So again, we're just iterating through. We have to use the move iterator because we've got the unique pointers. We can't copy them. Right. So this is what this ends up looking like in usage. One thing that we could do here is we could move this get devices call inside the constructor if we wanted to. I don't know whether that's better or worse, but I put it this way because in the thing we're going to look at, we're not going to be able to. So if this is something that's important, this is actually an advantage that the virtual approach gives us. Okay, so let's do this without virtual. So again, hopefully this is getting to feel familiar. We write a concept for our devices instead, right? So we've got some function update. It returns void, right? But here, we can actually bind find an env. There's nothing that prevents us from binding static types or static functions and concepts. So that feels like a win here. Our devices, largely the same. The one thing I will call out here is that we're not returning a pointer to base of any sort. We're actually a vector of pointers to base. We're returning just a vector of the things that we have. If we wanted to introduce that level of indirection here, we could hide it behind a pointer inside our implementation. That's not a problem, but we're not forced into it. So we end up, more exact types. Device manager. So we get some list of devices that might be stored, right, as our template parameter. We constrain that on C device so that we make sure that those all conform to the interface. We're going to reuse our tuple of vector pattern. I'll just call out, I don't think this is the only pattern in this space. This is the one that I find myself reaching for the most when I do this sort of thing, but there are definitely others. And like, think about the nature of your data when you're trying to construct these sorts of types. And hopefully something will become apparent, maybe after a lot of thought, but it's there. So update gets more complicated. We no longer have a single list of things, right? We've got our tuple. So we have to go and pull each of the vectors out of the tuple, and then we can iterate, right? And so we've got update device here that's gonna take take that vector and iterate through it. And then we've got our apply, which is going to go through each element of the tuple and expand it into the operation that you pass into that. And then we can just do an expansion of that over the comma operator. And now we're updating our devices. Again, there's an interesting property here in that we're not going in the order that our devices were supplied. We're going in the order that the types were supplied. Whether that's good or bad, again, comes down to your domain. There are certainly situations I've been in where there's been a particular device that's really important or really finicky or whatever, and I wanted to make sure that it was getting serviced with priority. Here you could put it as the first type in the type list, and that serves that. There's other cases where the ordering really does matter, and maybe this is a less sensible thing to reach for. So we've got that, right? We need to find some way to get all of our devices into this thing. So we write our getDevices function. Here I made it a private function. It needs access to the type list of the class. And so it's not really easy to call externally, which is what I was trying to point out on the end of the previous slide, where if you can't say device manager : get devices. You have to say device manager angle your list of all the things, close angle : and that's, if you have to repeat that type list and that type list is 50 types long, it's not fun to type. You can maybe hide that. In this case, I decided to kind of really call out that pain point by storing it here. But other than that, this is actually really nice. We can just directly construct the tuple. We don't have to provide the arguments because they're deduced with ctad. We just call find an env, and that provides us our vectors, and we just drop those straight in. Everything just kind of works here in that respect. And then to use that, I just call it in the constructor. You could definitely make this more efficient. Just an approach, right? Like the squeezing the juice out of it isn't the point of this talk. I'm trying to kind of think about the concepts. And that's our device manager. I think on the whole feels like a pretty big win to me in terms of just the implementation. The usage stays similar. You end up with that list of types. Hopefully, for the types of things you're doing this with, you can supply that list of types once, and then have that single place where you're maintaining it, and just pass it around, and then this becomes even simpler. I'd say pretty much equivalent to the other implementation. Yeah, that was the example. Any questions on that? Yeah. So is there a performance regression? It depends on, it's like, how are you using it? So The question is, what if you had 50 different types? Again, I think the answer is it depends on your domain. If you already had 50 different types and you're already densely populated, say you've got 5,000 elements in this list, and there's several of any given type, I'd be surprised to see a performance regression. But the answer to the question, like how does it perform, is always you have to measure, right? Like I can't give you a general answer to that. This is a tool that you should consider using to potentially gain performance. Question from online.
Yeah. How would you retrieve a device of a specific type?
Sorry, can you say that again?
How would you retrieve a device of a specific type?
So if you want to retrieve a specific device or a device of a specific type, you need to know to some degree what you're looking for. It comes down to your access patterns. A lot of the times with this, the specific type of the device that you're looking for, at which point you can use the same access method that we used to get elements out of to get the vector itself, right? If you know the type, then you can get the vector of that type and pull that whole vector out of the tuple, and then you can just operate on that vector as normal. And then from there, you have something that distinguishes the specific object that you're looking for from the rest of the objects that are of equivalent type.
Okay. There's one more related question. How do you deal with situations where an operation can yield one possible type from the list, but you cannot know the type until runtime? Specifically, how do you do this following your own rules from earlier in the presentation?
So at some point you have to, even if it's at runtime, you have to know that type, and then you can dispatch to whatever your lookup is. Like maybe you're doing a conditional dispatch. In the general sense, it's hard to answer that question, I think is kind of the answer. Because the specifics of how and when you know that type are very relevant. So like if you can, feel free to message me or find me in the hall or whatever. If you can present a specific example, I'm more than happy to talk through it.
Okay, thanks.
We've got 2.5 minutes. Any other questions? Yeah.
I just want to point out that the giant switch statement or the giant list of clauses, however you want to structure it, it's definitely very error prone, but it's not fair to count it against the virtual. You could basically write a type list and make a template package, generate the giant list of clause. It has nothing to do with using virtuals or not using virtuals. That's actually one place where the virtuals don't help, because it's like manual dispatch at runtime. It's a giant switch statement or something similar.
Yeah, so the comment is that you could potentially, in the virtual case, keep a list of types, and then like in the example where I did find env, you could use that list of types to take the same approach that I took in the case without virtual. I agree that that's possible. At that point, you do end up with kind of this hybrid thing where you end up maintaining the type list. And at the point that you're maintaining the type list, do you really want all of the virtual overhead as well? Maybe, maybe not.
Because you're maintaining the type list anyway. The list of these things within curly braces is the type list. It's all spelled out there. At that point, you cannot come in with a type that wasn't known when you compiled that thing and have it processed. Because at that point, all the types you could ever process are somewhere between those nested curly braces.
Sure. So the comment is that all of the types that get devices in the virtual case will find are already within the curly braces, and so functionally you're already maintaining that type list. Yeah, I agree. That's a fair point. Yeah. So the question is, if you're using C++17, is something like this possible? It's possible to bind so the only thing that's C++20 specific is CTAD and the use of concepts. So it's definitely possible. You can instead of concepts, you could use enable if. It gets really ugly really fast. I wrote a bunch of that earlier in my career, and I'm hoping I never have to do any of it again, sort of thing. Yes?
I've done enable if that scenario also, and I'm curious about enable if versus just static asserting on your like is in type list thing.
The same as any in the concept.
Yeah, I mean, you can write that without you can write a type trait for that, but I've done that and then use enable if. I'm just curious about enable if versus just like static asserting that it's matching your list.
So the question is, couldn't you do same as any without using a concept? Yes, you can do. You could write same as any as a type trait. I would say that's not where the types get messy. It's when you want to bind like multiple functions existing in an interface. That's where it really ends up getting ugly. All right, that's my time, guys. If people have more questions, I'm happy to hang out in the hall or again on the Discord. Thank you so much for coming, and yeah, enjoy the conference.